A premature baby who almost wasn't Isaac. Newton's life began in a fragile and almost miraculous way. He was born on December 25th, 1642, according to the Julian calendar in use in England at that time. In the Gregorian calendar, it would be January 4, 1643, in the small village of Woolsthorpe in Lincolnshire, England. His arrival in the world was marked by circumstances that made his survival improbable, which makes his life a true triumph over the adversities of nature. Newton's mother, Hannah Ayscough, was widowed before Isaac was born. Her husband, also called Isaac Newton, had died 3 months before his son's birth. Little Isaac was born prematurely, so small and weak that local stories said he could fit inside a 1-liter jar. These anecdotes may be exaggerated, but they reflect how critical his condition was at birth. Hannah's neighbors and relatives gathered, not to celebrate, but to prepare for the worst. They thought the baby would not survive the night. Hannah, however, did not lose hope. Although she was a peasant woman, she had an iron determination and a deep attachment to the child. For weeks she cared for him with extreme diligence, feeding him and protecting him from any temperature changes, which was crucial at a time when neonatal medicine did not exist. Miraculously, little Isaac not only survived but began to show signs of strength. The historical context of his birth is also worth mentioning. England was immersed in the English Civil War, a conflict between the Royalists, supporters of King Charles III, and the Parliamentarians, led by Oliver Cromwell. Although Newton was born in a rural environment, far from the battlefields, the political and economic instability of the time left its mark on the region. The Newton family owned a small farm which placed them in a modest but self-sufficient position. As a child, Isaac showed no obvious signs of being a genius. In fact, he seemed to be a solitary and abstracted child. He liked to build small gadgets with wood and other materials he found on the farm. According to accounts, he made miniature windmills, kites, and even rudimentary water clocks. These activities were more than simple games. They were the first manifestations of a curious and creative mind that sought to understand the world through observation and experimentation. A curious aspect is that Newton had a peculiar relationship with the religious stories that his mother and his environment instilled in him. At that time, the worldview was deeply influenced by religion, and the idea that everything in nature was divine work was unquestionable. Although Isaac respected these teachings, he also began to notice patterns and laws in the physical world that did not require supernatural explanations. He was a child who preferred to ask how and why, instead of simply accepting what he was told. The emotional isolation of his childhood and the limitations of his environment shaped his character. He often took refuge in himself, reading everything that fell into his hands. However, he was not an academic prodigy from the beginning. At school, he was known more for his explosive temper than for his intellect. On one occasion, after being hit by a larger classmate, Isaac swore revenge. Not only did he return the blow, but he also surpassed this rival in his studies, beginning to excel in mathematics and science. Childhood on the farm, a distracted genius. Isaac Newton spent his childhood in a rural environment, surrounded by fields, animals, and the typical tasks of a 17th century farm. Born in Woolsthorpe Manor, a village in the county of Lincolnshire, England, His home was a modest but respectable farm for the time. His childhood was marked by a mixture of isolation, emotional difficulties, and an overwhelming curiosity that would later become the spark of his genius. At the age of 3, Isaac experienced an event that would define his character: the departure of his mother, Hannah Asko, who remarried Barnabas Smith, a local clergyman. This second marriage meant that Isaac was left in the care of his maternal grandparents, which was an emotional blow that deeply affected him. Although there are no direct records of how he felt during this time, biographers agree that this early separation contributed to his introverted and reserved character. In his adulthood, Newton mentioned in his writings that he harbored resentment toward his stepfather, whom he never accepted as part of his family. The isolation of the farm, although difficult, had a positive side. It offered him a space of freedom to explore and observe the natural world. From an early age, Isaac showed an inclination for building things with his hands. He made miniature windmills, water clocks, and improvised lanterns with candles. His ingenuity was evident even in these childish games, which already demonstrated a mind oriented toward experimentation and mechanics. The rebellious student who didn't want to study. Isaac Newton's early academic life was marked by a surprising paradox. The man who would later be recognized as one of the greatest geniuses in human history began his education with a notable lack of interest. In his early school years, Newton showed no particular inclination towards studies and preferred to spend his time building artifacts or simply daydreaming, which initially led his teachers and classmates to underestimate him. Isaac attended primary school in Skillington, a village near his birthplace in Woolsthorpe. Although rural schools in the 17th century focused primarily on reading, writing, and basic mathematics, Newton found the lessons boring. His thoughts wandered, and he frequently entertained himself by drawing in the dirt or imagining fantastic stories. His initial disinterest was not a reflection of lack of ability, but rather of a mind that needed different stimuli than what traditional education could offer him. The significant change in Newton's education came when his mother decided to send him to King's School in Grantham at the age of 12. This school had a more advanced level and offered instruction in Latin, Greek, and mathematics, subjects that formed the basis of a humanist education in that era. However, Newton did not immediately adapt to this more rigorous environment. He spent more time devising small mechanical projects or building models that interested him than paying attention in class. One particular event marked the beginning of his transformation: an altercation with a larger classmate. This student hit and humiliated him, which enraged Newton. He decided to take revenge, not only physically, but also by academically surpassing him. Motivated by this competition, Isaac began to study intensely, dedicating long hours to reading and solving problems. This rivalry awakened in him a competitive spirit that he would maintain throughout his life. During his time in Grantham, Newton lived with an apothecary named William Clark and his family. There he had access to a small library where he found texts on natural sciences and philosophy that were not part of the school's official curriculum. He began to read avidly, exploring subjects such as astronomy, mechanics, and alchemy. Although these interests were outside his school tasks, they were fundamental to developing his scientific curiosity. His creativity did not go unnoticed among the inhabitants of Grantham. Isaac built a functional miniature windmill that could grind real grain. He also designed a portable lantern for his nighttime walks, which amazed his classmates. However, this behavior was not always well received. Many saw him as an eccentric and distracted child, more interested in his experiments than in the conventional activities of other children. At 16, Newton's educational trajectory faced an unexpected turn when his mother, Hannah, decided to take him out of school. His stepfather had died, and Isaac was now expected to take on the responsibility of managing the family farm. This decision went against the wishes of young Newton, who felt no interest in agricultural work. His clumsiness and lack of commitment to field tasks soon became evident. He spent more time doing mental calculations or studying the behavior of light in his room than taking care of animals or supervising crops. It is said that during an auction where he was supposed to sell agricultural products, Newton was so distracted doing mental calculations that he completely forgot his task. These constant distractions convinced his mother that farm life was not for him. Fortunately, his talent did not go unnoticed by some members of his family, particularly his uncle, William Ayscough. This uncle, who had studied at Cambridge, saw Isaac's intellectual potential and convinced his mother to allow him to return to school and continue his education. This was a decisive moment in Newton's life, as it marked the beginning of a path that would lead him to one of the most prestigious universities in the world. Back at King's School, Isaac began to stand out not only as the best student but also as someone with unusual and creative thinking. He became especially interested in mathematics, showing an exceptional ability to solve complex problems. His Latin teacher, seeing the level of his talent, recommended that Isaac apply to study at Trinity College, Cambridge, a suggestion that forever changed the young man's destiny. At Cambridge, Newton initially entered as a sizar student, which meant he had to work to pay for part of his studies. This involved tasks such as serving food to other more affluent students. However, far from demotivating him, this experience helped him develop a sense of discipline and hard work that would be key to his academic success. Although Cambridge was the epicenter of knowledge in England, Newton found that much of the material taught was outdated. Instead of limiting himself to following traditional lessons, he began to read on his own modern works by scientists such as René Descartes, Galileo Galilei, and Johannes Kepler. These readings expanded his perspective and led him to question established ideas, laying the foundations for his own revolutionary contributions to science. Newton's transition from a rebellious and disinterested student to a genius in the making illustrates how adversities and challenges can awaken latent talents. Throughout his life, he continued to face his rivals and challenge norms, maintaining the competitive spirit and determination he had cultivated in his youth. The Miraculous Year, Isolation, Plague, and Brilliant Discoveries. In 1665, Isaac Newton's life took an unexpected turn with the arrival of the Great Plague of London. This devastating outbreak of bubonic plague forced academic institutions in England to close, including Trinity College, Cambridge, where Newton was completing his bachelor's degree. While for many students this interruption was a forced pause in their studies, for Newton it became a period of intense creativity and reflection that would forever change the course of science. This period of isolation, which lasted approximately 2 years, is known today as his Miraculous Year, Annus Mirabilis. When the university closed its doors, Newton returned to his home at Woolsthorpe Manor, a quiet rural setting in the county of Lincolnshire. In this isolation, away from traditional academic distractions, he had the freedom to explore his most ambitious ideas. It was here where, without the direct guidance of his teachers, but armed with the texts and tools he had accumulated, Newton laid the foundations for some of his most important discoveries in mathematics, optics, and physics. One of the most outstanding achievements of the Miraculous Year was the development of a new branch of mathematics that would later be known as differential and integral calculus. Although Newton did not use this term, he called his method the calculus of fluxions. The central idea was to represent changes and rates of variation, a revolutionary concept for the time. Newton was deeply interested in how quantities change continuously, a topic he had encountered in his studies of geometry and physics. During his time in Woolsthorpe, he began to formalize a mathematical system to describe these relationships. He worked intensively with infinite series and developed techniques that allowed for calculating areas under curves and rates of change, fundamental tools for modern physics and engineering. Newton worked in solitude, writing his ideas in his notebooks without sharing them widely. Another field in which Newton made significant advances during his isolation was optics. Inspired by previous experiments with lenses and prisms, he conducted research to understand the nature of light. One of his most famous experiments consisted of passing a ray of sunlight through a triangular prism, breaking it down into a spectrum of colors. Newton observed that white light was not pure, as was believed at that time, but was composed of a set of colors that could be separated and recombined. This discovery broke with the traditional Aristotelian view, which held that colors were modifications of white light. From these experiments, Newton concluded that colors were inherent, properties of light itself and not side effects of the objects that reflected it. For Newton, these findings were deeply significant. He developed theories that would lay the groundwork for his work Optics years later, one of the most influential contributions to experimental physics in the 17th century. Perhaps the most iconic discovery of this period was the initial conception of the law of universal gravitation. According to popular history, Newton was sitting under an apple tree in the garden of Woolsthorpe when he saw an apple fall to the ground. Although the exact event may have been embellished over time, the anecdote illustrates a key moment of reflection. Newton began to wonder why objects fall toward the earth and if the same force could extend beyond, even to celestial bodies. Newton reasoned that the same force that made the apple fall could also be responsible for the moon's movement around the earth. This idea led him to develop a theory that unified seemingly disconnected phenomena. Gravity not only explained terrestrial movements, such as the falling of objects, but also celestial ones, such as planetary orbits. Although during this period he did not fully formulate the laws of motion and universal gravitation, he laid the conceptual foundations that he would later develop in his masterpiece, the Principia Mathematica. His ability to connect ideas and work in solitude was fundamental to this advance. The isolation forced by the plague allowed Newton to work without the distractions of formal academic activities or the pressures of social expectations. At Woolsthorpe, he had time to think deeply and experiment freely, something that probably would not have been possible in the more structured environment of Cambridge. Additionally, this period was a testament to Newton's self-discipline and capacity for concentration. Despite the adverse circumstances, he transformed isolation into an opportunity to delve into the fundamental questions that intrigued him. His notebooks from this period are filled with annotations, diagrams, and calculations that show a mind working at the limit of its capacity. When an apple changed history. It was the summer of 1666, a year after the bubonic plague had forced Isaac Newton to return to his family home in Woolsthorpe Manor. There, far from the bustle of Cambridge and surrounded by the silence of the English countryside, Newton lived days of intense solitude, immersed in his thoughts. Although the outside world was plunged into chaos, in his mind, the most fundamental questions about nature and the universe were about to find answers. One warm afternoon, Newton decided to go out to the garden. The days were long and peaceful, and the wind whispered through the trees. He often found in the open air a refuge to order the ideas that haunted him during hours of study in his room. As he walked among the apple trees growing on the property, something happened. An apple fell from one of the nearby trees and gently rolled until it stopped at his feet. Newton paused. He looked at the apple, as ordinary as any he had seen before, but instead of picking it up and continuing his walk, his mind filled with questions. Why do apples always fall downward? What draws them to the ground? Is this force exclusive to Earth, or could it extend much further, even to the sky itself? The scene might have gone unnoticed by anyone else. A falling apple was not something extraordinary, but for Newton, nothing was trivial. He had spent years challenging traditional explanations and developing a deeply analytical approach to understanding the world. This simple apple became the catalyst for one of the most revolutionary ideas in history. As he reflected on the falling apple, his gaze turned to the sky. The moon shone palely on the horizon. Newton, in his incessant curiosity, wondered if the same force that made the apple fall could also be responsible for keeping the moon in orbit around the Earth. Until that moment, the laws governing objects on Earth and celestial movements were seen as separate phenomena. However, Newton began to connect both worlds. What if gravity was not a local force, but a universal force that influenced all bodies, large and small, anywhere in the cosmos? The falling apple became the starting point for a series of deductions. Newton began to imagine how this force would work. It must depend on the masses of the bodies involved and the distance separating them. The larger the mass, the greater the attraction. The farther apart they were, the weaker the force would be. In the days that followed, the image of the apple did not leave his mind. As he walked through the hallways of Woolsthorpe or sat writing by a dim candle, his thoughts revolved around this invisible force. The connection between the apple and the moon seemed not only plausible, but inevitable. At Woolsthorpe, Newton had no access to libraries or mentors to guide him. However, what he did possess was a keen instinct for formulating the right questions and the patience to find answers. For months, he worked meticulously, developing concepts that would forever change our understanding of the universe. While the rest of the world dealt with the plague and uncertainty, Newton traced equations and diagrams trying to unravel the secrets of gravity. The solitude of Woolsthorpe provided him with the time and space necessary to advance his thoughts without external interruptions. The myth and reality of the apple. The famous story of the apple that hit Newton's head is in large part a popular myth. It was popularized by William Stukely, a close friend of Newton, who years later recounted how Newton told him about the episode during an informal conversation. According to Stukely, the apple did not hit Newton, but it did inspire him profoundly. Although the real event was probably not as dramatic as it is told, the essence of the story captures something fundamental about Newton's genius, his ability to observe everyday phenomena and transform them into profound questions about the laws of the universe. In his solitude, Newton saw in the apple not just a physical object, but also a symbol of his quest to understand the natural order. Each time he looked at that tree in the garden of Woolsthorpe, he must have felt a spark of pride and determination. What was a simple fruit for others became for him a bridge to the stars. The idea of universal gravitation, born from this moment of reflection, not only explained why apples fell, but also why planets orbited the sun and how tides moved. Newton's theory unified Earth and sky under a single set of laws, something unprecedented in the history of science. Many years later, Newton would publish these ideas in Philosophia Naturalis Principia Mathematica, his masterpiece that would lay the foundations of classical mechanics. But it all began in Woolsthorpe, with an apple and a relentlessly curious mind. The falling apple teaches us that great ideas don't always emerge in sophisticated laboratories or amid the bustle of universities. Sometimes nature itself, in its simplicity, offers the necessary clues to unravel its secrets. Newton showed us that curiosity, observation, and perseverance can transform the ordinary into the extraordinary. That apple, which fell one afternoon, in Woolsthorpe, not only changed Newton's life, it changed the way humanity understands its place in the cosmos. Newton, the secret alchemist. The sun was just beginning to appear on the horizon when Isaac Newton lit the candle on his work table. It wasn't his usual desk where he performed mathematical calculations, nor the bench where he built optical experiments. This was a different place, almost hidden within his house in Cambridge. Glass flasks, coloured powders, scrolls with incomprehensible symbols, and a strange metallic smell filled the small room. There, Newton was not the rigorous scientist who analysed the movement of planets. He was an alchemist, an explorer of the most ancient and mysterious secrets of matter. During the 17th and 18th centuries, alchemy was at a point of transition. Although it was still seen by many as a mystical and archaic practice, it was also a precursor to modern chemistry. The promise of turning lead into gold, discovering the elixir of life, or unraveling the secrets of matter remained fascinating even for some of the most prominent intellectuals of the time. Newton, a deeply reserved man, found in alchemy a way to explore questions that went beyond physics and mathematics. For him, alchemy was not simply a quest for wealth or immortality, it was a way to understand the hidden forces that united the universe, the same forces that governed gravity and the movement of celestial bodies. Few knew this facet of Newton. In his small laboratory, he worked in absolute secrecy, aware that revealing his interest in alchemy could damage his academic reputation. At that time, alchemy was associated with charlatanism and esoteric practices. However, for Newton, it was a discipline that required a combination of rigorous observation, intuition, and patience, qualities he had already demonstrated in his scientific work. He spent hours heating metals, mixing substances, and carefully noting his observations in a cryptic language that only he could understand. His alchemical manuscripts, which would later be rediscovered centuries afterward, were full of references to ancient texts and detailed experiments. Newton devoutly read the works of alchemical authors such as Hermes Trismegistus and Robert Boyle, looking for clues about the nature of matter and transmutation. One of the elements that fascinated Newton was mercury, a liquid metal that seemed to defy the known laws of nature. In his experiments, Newton heated and mixed mercury with other compounds, observing how it changed in form and color. He believed that mercury could be a key to understanding the transmutation of metals, the quintessential alchemical process. However, working with mercury was dangerous. The toxic vapors affected the health of alchemists, and Newton was no exception. Some historians believe that his obsession with alchemy and his prolonged exposure to mercury contributed to the episodes of erratic behavior he experienced in his later years. For Newton, alchemy was not just an experimental science, it was also a spiritual quest. He believed that the secrets of matter were deeply connected with divine mysteries. In his mind, the universe was like an elaborate clock designed by a supreme creator, and alchemical principles were part of that design. Newton saw in alchemy a continuity with his studies of the Bible and theology. He spent years trying to decipher hidden codes in the scriptures, convinced that they contained clues about the secrets of the universe. In the same way, he searched alchemical texts for ancient truths that could complement his vision of the cosmos. Newton's dedication to alchemy was a well-kept secret during his life, but came to light after his death. In 1936, economist John Maynard Keynes acquired a large number of Newton's manuscripts at an auction. Upon examining them, Keynes was surprised to discover that a significant portion of Newton's writings was not dedicated to science, but to alchemy and theology. Keynes described Newton as the last of the magicians, the last of the Babylonians and Sumerians. For some, this revelation was disconcerting. How could the man who had developed the foundations of modern physics dedicate so much time to a discipline that many considered pseudo-scientific? However, for others, Newton's alchemy was not a contradiction, but an integral part of his genius. In an era when the barriers between science, philosophy, and spirituality were much more permeable, Newton saw all these disciplines as aspects of the same quest, to understand the laws that governed the universe. Newton's alchemy was not simply a search for gold or an attempt to prolong life. It was a deep exploration of the nature of matter and the forces that shape it. He believed that matter was not static, but could be transformed under the right conditions, a concept that, centuries later, would find an echo in modern chemistry and quantum physics. Although Newton did not succeed in transmuting metals or discovering the elixir of life, his alchemical experiments and reflections influenced his scientific thinking. The idea that the universe was united by universal laws, visible and invisible, was reflected in both his alchemical work and his discoveries about gravity and motion. The figure of Newton as an alchemist remains an enigma. His alchemical manuscripts, many of which remain undeciphered, contain a treasure trove of ideas and experiments that reveal a lesser-known facet of his brilliant mind. Some suggest that his alchemical studies were much more advanced than has been recognized, while others see them as an eccentric deviation from his true genius. What is indisputable is that Newton, the man who unraveled the laws of motion and gravity, never stopped exploring the unknown. Whether through telescopes pointing toward the stars or bubbling flasks in his laboratory, Newton dedicated his life to pursuing the deepest truths of the universe. And so, in the shadows of his laboratory, between the glow of flames and the shine of Mercury, Newton was not just seeking gold. He was seeking the keys to the cosmos, convinced that the same divine spark that moved the planets could also be found in the smallest particles of matter. The Mathematical Duel with Leibniz. It was a rainy day in October 1676 when Isaac Newton received a letter from a European correspondent, one with whom he had already exchanged some ideas and who, until that moment, seemed to share his scientific vision. However, in that sealed envelope there were not only kind words, but a bomb that would profoundly alter his world. The name that appeared on the letter was that of Gottfried Wilhelm Leibniz, a German mathematician and philosopher. That man, far from being unknown to Newton, had been developing in parallel a mathematical theory similar to Newton's, differential and integral calculus. But in that letter the tone was clear and direct. Leibniz was claiming authorship of one of the most revolutionary mathematical ideas in history. This would be the beginning of one of the most tense and controversial Episodes in the history of science, the famous duel between Newton and Leibniz, a struggle of egos, identities, and scientific reputations that would mark not only their careers, but the way mathematics and science would be viewed in the centuries to come. The genesis of calculus. Although he was not the first to have an idea of the mathematics that would later develop as calculus, Newton was one of the main drivers of its creation. Its genesis began in the late 1660s when Newton was more focused on his work on the law of universal gravitation and his investigations in optics. However, as he addressed the problem of forces and movements of bodies, he realized that traditional arithmetic and the geometry of his time could not accurately describe the phenomena of acceleration and continuous change that he observed in nature. In this way, Newton developed a completely new mathematical notation to understand instantaneous change, which would later be known as calculus. Newton began to develop his own version of what we now understand as differential calculus, with his fluxions and fluent fluxions. However, he did not immediately publish his discoveries, largely due to his reserved nature and his dedication to other branches of science. Newton let his work mature in obscurity. On the other hand, Leibniz, a German scholar, was working on his own approach to solving problems related to tangents, the area under a curve, and change in general. Leibniz, unlike Newton, was not so involved in the world of physics or astronomy, but concentrated more on pure mathematics. He developed a much more accessible notation system than Newton's, using symbols that are still used today, such as the integration sign. Leibniz began publishing his findings in 1684, taking a decisive step in opening the debate over the paternity of calculus. The trigger of the conflict. It was in 1676 when Leibniz, upon receiving news of Newton's work, wrote to some of his British mathematical colleagues, commenting on his own discoveries about calculus. It was an apparently innocent letter, but one that soon triggered a storm. Newton, who had already been working on his own mathematical ideas, felt deeply insulted by the suggestion that someone else might have developed calculus without giving him proper recognition. Although Leibniz never explicitly claimed authorship of the entire concept, the fact that his results coincided with Newton's, in many aspects in his opinion, was not mere coincidence. The conflict erupted when it was discovered that Leibniz had received letters from British mathematicians who, apparently, were familiar with Newton's work on calculus. According to Newton, some of these mathematicians, especially John Collins, had obtained the results of his work without his permission and shared them with Leibniz. The English mathematicians saw in this exchange of information a direct plagiarism of his ideas. The War of Letters. What followed was a series of accusations, responses, and disagreements that extended for many years. In 1679, Newton, furious and feeling threatened, requested that the Royal Society of London, of which he was a member, investigate the matter. For this, he appointed his friend and follower, the philosopher of science Thomas Bayes, to conduct an investigation on the matter. The Royal Society's investigation not only served to fuel discord, but was clearly biased toward Newton. The president of the Royal Society, also scientist Robert Hooke, had a tense relationship with Newton, but even so the investigation finally ruled that Leibniz had copied Newton's ideas, a conclusion that was based on the versions of Newton's documents that had been found. However, Leibniz did not remain silent. He responded immediately, accusing Newton of being the real plagiarist, alluding to the possibility that Newton's ideas were based on the works that Leibniz had published. The exchange intensified, with Newton and Leibniz seeking support from other scientists for their respective versions of the facts. The conflict between Newton and Leibniz reached such intensity that for many years mathematics was divided. While Newton's followers, such as Samuel Clerk, vehemently defended the superiority of his version of calculus, Leibniz's supporters, such as John Bernoulli, backed him at all costs, although both mathematicians continued working on the development of calculus during their lives. The confrontation became a personal war that overshadowed their achievements. This conflict had lasting repercussions. For a long time, Newton's calculus was relegated to obscurity in much of continental Europe, while Leibniz enjoyed recognition for his version. It was not until the late 18th and early 19th centuries, after the death of both, when mathematicians began to recognize that both had made fundamental contributions to the development of calculus, and that their approaches were not mutually exclusive, but complementary. The modern theory of calculus is, in many respects, the result of the synthesis of the two approaches. Newton invented calculus, but didn't publish it. The story of Isaac Newton is one of the most well-known in science, but there is a chapter of his life that has generated a great deal of speculation and controversy, a mystery that is still debated. Why did Newton, despite having invented calculus, not publish it in his time? Calculus, that fundamental mathematical tool that has shaped everything from theoretical physics to modern engineering, is one of the pillars on which the world of science is built. However, in Newton's case, his discovery was marked by secrecy and delay in its dissemination. This chapter of his life, full of tensions and difficult decisions, is as fascinating as the results of his research themselves. The beginning of a revolutionary discovery. By the late 1660s, Newton was already a man with an exceptionally curious mind capable of unraveling the mysteries of light, color, and movement. After returning to his home in Woolsthorpe, following the temporary closure of Cambridge University due to the bubonic plague of 1665-1666, Newton immersed himself in a whirlwind of research, experiments, and notes that would last for years. It was during this period, known as his Miraculous Year, when he developed the fundamental ideas that would later lead him to formulate his laws of motion and the law of universal gravitation. But in his notebooks, he also began to develop a revolutionary theory, a new way of understanding change, calculus. Newton's calculus was born from his attempt to understand the movement of celestial bodies and how forces acted upon them. He realized that existing mathematics could not adequately describe the movement of planets, the behavior of forces in their continuous change. In this way, he began to create a new form of mathematics that would allow him to work with infinitesimal quantities, the concept of derivatives and integrals, the two pillars of modern calculus. Newton called his discovery the method of fluxions and developed it primarily as a tool to solve problems in physics, especially in the area of gravitation. Despite the fact that Newton was developing a profoundly novel theory and intended to publish it, his introverted and reserved nature played a fundamental role in these discoveries not being shared with the scientific community at that time. Newton, as was usual for him, preferred to work alone and in isolation, without worrying about social expectations or demands. Although in his private letters and personal notes he had already referenced calculus, his first significant publication would not include an exposition of this method. Although Newton had begun to develop his calculus around 1666, it wasn't until years later, when mathematicians throughout Europe began to notice Leibniz's work, that the history of calculus would take a dramatic turn. Leibniz, a German mathematician who was also investigating questions related to change and movement, published his own results on calculus in 1684, based on a different approach and with a much simpler and more comprehensible notation than Newton's. Leibniz, who was a more extroverted and sociable man than Newton, published his discoveries quickly, without the same reservation that Newton had shown. Leibniz used his modern notation of integration and his derivative symbol, which quickly became the standard in European mathematics. Meanwhile, Newton continued working in his own notebooks but did not publish anything formal. The absence of a work that clearly defined and organized calculus left the field open for Leibniz, who quickly gained recognition for his development of calculus, especially in continental Europe. This delay in Newton's publication became the center of a fierce controversy that divided the mathematical community for years. As Leibniz began to gain prestige and acceptance, some British mathematicians, including John Collins and Samuel Clarke, began to link Newton's name to calculus and claim that Leibniz's discovery was based on Newton's earlier work. Leibniz, for his part, did not remain silent and vehemently defended his right to the paternity of calculus. This exchange of accusations and the lack of a formal publication by Newton triggered what would be one of the greatest scientific confrontations in history, the dispute over the authorship of calculus. The question of why Newton did not publish his discovery remains a subject of debate. There are several theories about the reasons that led Newton not to make his work on calculus public. One of the main reasons pointed out is Newton's reserved nature. He was a deeply introverted man, often absorbed in his work without concern for fame or recognition. Additionally, Newton was completely immersed in other scientific and philosophical projects, such as his research on optics, gravitation, and mathematics. While his discoveries about calculus were fundamental, he considered them secondary tools compared to his studies on the laws of motion and gravity. Another theory is that Newton feared that by making his work public, he could have been attacked or criticized by the scientific community, something he avoided as much as possible. In that era, scientists were often very protective of their discoveries and shared ideas only when they were absolutely sure of their validity. This attitude, combined with his distrustful and competitive character, caused Newton to postpone the publication of calculus. Furthermore, the lack of a clear and comprehensible notation may have influenced the decision not to publish. Newton used a more complicated and less accessible notation than Leibniz, and although their results were equivalent, the complexity of his presentation could have made the scientific community of the time not appreciate its importance. Leibniz, on the other hand, was more effective in simplifying notation, and in this way facilitated the understanding of his own work. Finally, it was in 1704, after years of struggle for authorship and recognition, when Newton published his most complete work, Philosophiae Naturalis Principia Mathematica, a treatise that established the foundations of modern physics. However, this work did not include a detailed explanation of calculus. It was only in 1713, long after Leibniz had published his work, when Newton decided to publish his Method of Fluxions, a text in which he described his system of calculus. But this was presented in a way that could not have been understood by many mathematicians of the time, which resulted in limited dissemination. The end result was a decades-long struggle over who had the right to be recognized as the inventor of calculus. Newton, despite having been the true inventor of calculus, never obtained public recognition for his work. Leibniz, for his part, went down in history as the founder of calculus, largely due to the speed with which he made his ideas public and the clarity of his notation. The controversy continued for years, even after the death of both men. It was only much later, as mathematics developed and the contributions of both scientists were combined, that it was recognized that calculus was the result of the parallel work of two brilliant minds. An astronomer obsessed with light. Often, the history of science is written not only with great discoveries, but also with persistent questions that trouble those who dare to challenge the explanations of their time. Isaac Newton, the same man who had laid the foundations of classical physics, was not just a brilliant mathematician and physicist, but also an astronomer deeply obsessed with a fundamental question: the nature of light. For Newton, light was much more than an everyday phenomenon. It was the key to understanding the universe. Newton's obsession with light began during his time at Cambridge, but it was throughout his life that he dedicated a considerable amount of time to this mystery. In the late 17th century, the predominant conception of light in Europe was dominated by the ideas of ancient Greek philosophers, especially Aristotle's theories and the principles of optics from Euclid and Ptolemy. However, these approaches were not enough for Newton, who was not satisfied with traditional answers. Instead of accepting established notions, Newton felt that the key to understanding the world had to be found by observing the phenomenon directly, with the meticulousness of an experienced scientist. Very early in his career, Newton encountered a crucial question. What is light? Is it a substance, or is it simply a phenomenon of vision? In the early 17th century, science still didn't have a clear answer, and previous explanations were mostly philosophical or geometrical. For Newton, the mystery of light was intriguing enough to occupy him for years, and his quest would lead him to some of his most notable discoveries. The experiment with the prism. In 1666, Newton conducted an experiment that would become a milestone in the history of optics. As science began to undergo a transformation toward an experimental approach, Newton departed from accepted theories and decided to test his own ideas. Using a glass prism, he placed this object in front of a beam of white light. In doing so, he observed a fascinating phenomenon. The white light broke down into a spectrum of colors. For years, the notion that white light was pure had been an accepted concept, but this discovery seemed to challenge that belief. Newton, puzzled but intrigued, repeated the experiment again and again, verifying his result. It had become clear to him that white light was not homogeneous but a mixture of different colors. This was the beginning of a new theory about the nature of light. The idea that light was composed of particles or corpuscles of different colors. By breaking down light into its spectrum, Newton came to the conclusion that colors were not simply a visual property, but an integral part of the nature of light itself. The corpuscular theory. After his experiments with prisms, Newton began to develop his own theory of light. He believed that light was made up of tiny particles, which he called corpuscles. This corpuscular theory was revolutionary in its time, as it challenged the wave view of light, defended by other scientists like Robert Hooke. While Hooke and his followers maintained that light was a wave, Newton firmly believed that light was a stream of very small particles which interacted with the objects they touched, producing phenomena such as reflection and refraction. Although Newton's corpuscular theory seemed to have convincing experimental support, contemporary scientists gave little attention to his ideas. The prevailing perception of light as a wave had been defended by philosophers like René Descartes and many of the leading thinkers of the time. Although Newton's theory was accepted by some, many other thinkers, like Hooke, attacked the corpuscular hypothesis, arguing that light should be treated as a wave, an idea that would dominate science for centuries. The work in optics, and Newton's legacy. Despite the criticism, Newton never abandoned his work on light. In 1704, after years of experimentation, he published his most important work on the subject, optics. In this book, Newton presented not only his theories about light and colors, but also a series of meticulous experiments that supported his vision. Optics not only established the corpuscular theory, but also introduced revolutionary concepts about optics, reflection, refraction, and the nature of colors. The work, although it did not have the same immediate impact as his Principia Mathematica in the field of physics, laid the groundwork for the study of modern optics. One of Newton's great contributions in optics was his explanation of the phenomenon of dispersion, in which white light separates into various colors when passing through a prism. Newton also offered a detailed analysis of the reflection of light and developed a theory of colors based on the idea that colors were the result of the different speeds with which light corpuscles interacted with the surfaces of objects. In many ways, optics was a manifesto of Newton's obsession with light, and the work would become the cornerstone of experimental optics for centuries. The competition with Hooke and the struggle for scientific truth. Newton's obsession with light not only led him to develop new theories, but also to a confrontation with other scientists of the time. One of Newton's biggest rivals in the field of optics was Robert Hooke, an engineer and scientist who had proposed his own theory about light. Hooke, who had also made important discoveries in the field of optics, had maintained that light was a wave which directly contradicted Newton's corpuscular theory. The confrontation between Newton and Hooke was tense and personal. Over the years, both scientists exchanged criticisms in their writings, with Hooke accusing Newton of plagiarizing his ideas about light. Newton, for his part, defended himself energetically, although the confrontation was never fully resolved. The conflict between these two great scientists underscores the fierce nature of competition in 17th century science, when ideas could be as valuable as the reputation of those involved. Newton's legacy in optics. Newton's obsession with light not only had an impact in his time, but also left a lasting mark on science. Despite the controversy with Hooke and the lack of immediate acceptance of his corpuscular theory, Newton's work on optics was fundamental to the development of science in subsequent centuries. His theory of colors and work on the dispersion of light would influence generations of scientists, including figures such as Thomas Young and Augustin Jean Fresnel, who, centuries later, developed the theory of light as a wave, but also built upon Newton's experiments. Additionally, Newton's experimental approach in optics marked a significant difference in the scientific method. While many of his contemporaries continued to approach science philosophically, Newton used rigorous experimentation to test his hypotheses. His practical approach in optics laid the foundations for the future of scientific research and became a model for generations of scientists who came after. The reflecting telescope scandal. Isaac Newton, the genius who had revolutionized science with his laws of motion and theory of gravity, was not only a renowned mathematician and physicist, but also an innovator in the field of astronomy. His work in optics and his study on the nature of light were fundamental to his career. But there was a chapter in his life that would mark a milestone in the history of science, one that would have an impact beyond his theories and experiments: the development of the reflecting telescope. This invention not only changed astronomy, but also triggered a series of controversies and scandals that involved some of the most influential scientists of his time. An invention so brilliant, which should have been received with applause, became the center of a fierce dispute, pitting Newton against some of the most important names in English science of the time. How could an invention that marked such a great advance in optical technology become a battlefield of egos, jealousy, and power struggles? The story of the reflecting telescope is a story of innovation, intrigue, and scandal. The astronomical context of the era. In the 17th century, astronomy was in a period of impressive advances. The backdrop of this era was marked by the work of figures such as Galileo Galilei, who had perfected the refracting telescope, and Johannes Kepler, who had proposed the laws of planetary motion. However, these refracting telescopes, which used lenses to focus light, had significant limitations. Lens telescopes had the problem of chromatic aberration, a distortion of the image that occurred because the colors of light separated when passing through the lens. This distortion severely affected the quality of astronomical observations and limited the capabilities of telescopes of the time. In this context, Newton, always looking for a way to improve human knowledge and challenge the limitations of his time began to think of a solution. If lenses could distort images, why not use a mirror instead, which would not produce chromatic aberration? It was a radical idea, but Newton, as always, was willing to break established molds. The birth of the reflecting telescope. In 1668, at just 26 years old, Newton unveiled one of his most innovative inventions, the reflecting telescope. The idea behind this telescope was simple but brilliant. Instead of using lenses, as refracting telescopes did, Newton employed a concave mirror to reflect light toward an eyepiece. This design eliminated chromatic aberration, a problem that had affected previous telescopes for centuries and produced much sharper and clearer images. Newton's reflecting telescope was the first of its kind in the history of science, and it was a crucial advancement for astronomy. Thanks to its design, astronomers could observe the skies with greater clarity and precision than ever before. The image provided by the mirror telescope was brighter and more precise, which meant that astronomers could see more details and obtain more accurate information about celestial bodies. This invention was so amazing that it quickly became a revolution within the field of astronomy. The reflecting telescope not only improved observational capability, but also inaugurated a new era in telescope construction. Although the concept of a reflecting telescope existed in some previous theories, it was Newton who effectively put it into practice, demonstrating its viability and utility. The reception of the invention and first disagreements. Despite the brilliant advance that the reflecting telescope represented, its reception was not as warm as one might expect. Instead of being acclaimed as the innovator he was, Newton encountered unexpected resistance, especially in his own country, England. The scientific community of the time, although made up of brilliant men, was not willing to easily accept a new technology, especially when it came from a man like Newton, whose reputation was beginning to grow. First, many astronomers were skeptical about the usefulness of the reflecting telescope. The idea of using a concave mirror instead of lenses was completely new, and many thought that the quality of the image would not be sufficient to make high-precision astronomical observations. Despite the successful tests that Newton conducted with his telescope, many remained firm in their skepticism. However, the true controversy arose when other scientists began to make claims about credit for the invention. The scandal with scientific authorities. The scandal began when Newton's opponents, including some of the most prominent scientists of the time, began to attack his invention. Although Newton did not seek public recognition, his reflecting telescope was so revolutionary that other scientists could not ignore it. The problem lay in the fact that while Newton had made his invention in 1668, it was not until several years later that it was more widely disseminated. During that time, several other scientists began to experiment with mirror telescopes, which generated controversy over who had the idea first. One of Newton's main rivals in this conflict was the astronomer and philosopher Robert Hooke, a member of the Royal Society and a known critic of Newton. Hooke, although he had not worked directly on the construction of reflecting telescopes, was one of those who challenged Newton's credit for the invention. Hooke maintained that Newton had not invented the reflecting telescope, but had simply improved on the previous ideas of other scientists. Despite the evidence being on his side, and Newton's reflecting telescope being clearly superior to any previous attempt, the dispute between the two men intensified. The conflict reached a high point when Hooke publicly accused Newton of appropriating others' ideas. This unleashed a series of exchanges in the Royal Society where the discussion turned into a personal debate about the authorship of the reflecting telescope. The confrontation between Newton and Hooke was fierce, and it was not limited to the question of the reflecting telescope. Both men repeatedly clashed on other scientific topics, and their enmity became one of the most bitter episodes in the history of science. the politics and jealousies of science. The reflecting telescope scandal was not just a clash of scientific ideas, but also a struggle of egos and power in the scientific community. In Newton's time, science was far from being the collaborative field we know today. Rivalries between scientists were not just a matter of disagreement about the truth, but often involved questions of prestige, power, and recognition. Newton, a deeply introverted man, did not react well to the public criticisms of Hooke and other rivals. In his reserved and meticulous manner, Newton did not want to participate in public discussions. However, his work and discoveries were so transcendental that his rivals felt threatened, and the reflecting telescope became one of the cornerstones of the dispute. The legacy of the reflecting telescope. Despite the controversy, Newton's reflecting telescope left an indelible mark on the history of science. Today, reflecting telescopes are the basis of almost all major modern astronomical telescopes. The idea of using mirrors instead of lenses allowed telescopes to be made larger, more powerful, and more accessible to astronomers, resulting in countless discoveries in the field of astronomy. The reflecting telescope scandal, with all its rivalries and disputes, faded with time. Although Newton did not live to see the resolution of this conflict, his invention was consolidated as one of the most important contributions to modern science. And, despite the jealousies, disagreements, and struggles for recognition, Newton's reflecting telescope remains a symbol of human capacity to challenge limits and change the course of science. Newton and his enemies, the relentless scientist. The figure of Isaac Newton is undeniably that of a genius, but his scientific greatness was not exempt from personal conflicts. In the intellectual world of the 17th century, disputes were common, but Newton seemed to attract them with unusual intensity. It wasn't just that other scientists envied his talent, it was that Newton had a perfectionist, reserved, and often vengeful personality. These characteristics made him a formidable adversary. His enemies were not few, and each confrontation left deep marks not only on him, but also on the scientific community of the time. From an early age, Newton showed himself to be a solitary and distrustful man. His childhood, marked by the absence of his father and a distant relationship with his mother, contributed to shaping his reserved character and his inclination to work in isolation. For Newton, the outside world was a place full of dangers, criticisms, and possible betrayals. This, combined with his insatiable thirst for knowledge, led him to develop an obsession with protecting his work and controlling every aspect of his intellectual life. When Newton began to stand out at Cambridge, his distrustful nature could already be glimpsed. He worked tirelessly, but rarely shared his discoveries. For years, he kept secret his advances in calculus, optics, and mechanics, fearing that others would appropriate his ideas. This precaution, although understandable, was also the seed of many of his future disputes. The rivalry with Robert Hooke. One of Newton's first and most bitter confrontations was with Robert Hooke, an influential member of the Royal Society and a key figure in English science. Hooke was a brilliant man, but he also had an arrogant personality and a tendency to claim credit for ideas he had barely worked on. When Newton began to present his discoveries in optics, including his revolutionary theory about light and colors, Hooke was quick to attack. Hooke maintained that Newton had based his theory on previous works, especially his own. Although Hooke's accusations were unfounded, his position in the Royal Society gave weight to his words. Newton, for his part, was not known for accepting criticism easily. What began as a scientific disagreement soon became a personal enmity. Newton avoided attending Royal Society meetings for years to avoid encountering Hooke. and when he finally assumed leadership of the institution, he made sure to minimize the influence of his old rival, the duel with Leibniz over calculus. If the conflict with Hooke was intense, the dispute with Gottfried Wilhelm Leibniz was even fiercer. This battle, which extended for decades, revolved around the invention of calculus. Both Newton and Leibniz developed independently this powerful mathematical language that would revolutionize science. However, when the works of both began to be published, the inevitable question arose: who invented it first? Newton had developed his version of calculus in the 1660s, but, as was usual for him, he did not publish it immediately. Leibniz, on the other hand, began to work on calculus years later, but was the first to publish it in 1684. This led many to think that Leibniz was the true inventor. For Newton, who considered his invention one of the most important achievements of his life, this confusion was intolerable. The dispute intensified when the Royal Society, under Newton's direction, published a report that defended Newton as the true creator of calculus and accused Leibniz of plagiarism. Although the report was presented as impartial, the reality was that Newton had supervised its drafting, making sure to tip the scales in his favor. Leibniz's reputation was deeply damaged, and the conflict left a shadow over the lives of both men. Newton, the vengeful president of the Royal Society. In 1703, Newton assumed the position of president of the Royal Society, consolidating his position as the most influential scientist in England. However, his leadership was not without controversy. Newton used his position to consolidate his legacy and, in some cases, to settle scores with his enemies. One of the darkest episodes of his presidency was his treatment of John Flamsteed, the royal astronomer. Flamsteed had been working for years on a detailed stellar catalogue, but Newton, eager to use the data in his own works, tried to force its publication before Flamsteed was ready. When Flamsteed resisted, Newton used his power to remove him from his position and publish the catalogue without his consent. Although Flamsteed eventually managed to recover his work and destroy the unauthorized copies, the damage to his relationship with Newton was irreparable. The loneliness of genius. Despite his successes and his power, Newton was not a happy man. His constant confrontations and his inability to trust others left him isolated. Even his closest allies described him as a difficult man, obsessed with his reputation and his legacy. In his later years, Newton dedicated himself to revising his works and ensuring that his version of events prevailed. Although he managed to consolidate his place in history, the personal cost of his relentless pursuit of truth was enormous. The Principia, the book that explained the universe. In the summer of 1687, an exceptional manuscript came to light, a book that would forever change the way humans understood the cosmos. Its complete title was Philosophiae Naturalis Principia, Mathematica, but the world would know it simply as Principia. Its author, Isaac Newton, was already a renowned academic, although unsociable and reserved. However, with this work, his place in history would be secured. Principia was not just a book. It was a masterpiece that consolidated the laws governing the universe and marked the height of the scientific revolution. The story of Principia began long before the manuscript was written. Newton had spent years researching the forces that govern the movement of celestial bodies. Inspired by the work of giants like Copernicus, Kepler, and Galileo, Newton sought answers to questions that no one had satisfactorily resolved. What kept the planets in orbit around the sun? What forces made objects fall to the ground? These questions obsessed him. In 1666, during the plague that forced him to leave Cambridge and take refuge in Woolsthorpe, Newton had a miraculous year. There, in solitude, he developed the foundations of his theory of universal gravitation. It is said that the famous fall of an apple inspired him to relate the force that attracted objects toward Earth with the one that kept the Moon in orbit. Although the anecdote is simplified, the concept was revolutionary. A single force, gravity, could explain both terrestrial and celestial movements. However, Newton did not publish these ideas immediately. He was a meticulous, almost obsessive man and preferred to perfect his theories before making them known. An external impulse was necessary for the world to finally know Principia. The role of Edmund Halley. In 1684, Edmund Halley, a young and brilliant astronomer, visited Newton in Cambridge. Halley was interested in solving a problem that had puzzled scientists. What type of curve did planets follow in their orbits? He had heard rumors that Newton already had an answer. During their meeting, Newton casually responded, "An ellipse." Intrigued, Halley asked for proof, and Newton promised to send him his calculations. A few months later, Halley received a manuscript titled De Motu Corporum in Gyrum, on the motion of bodies in orbit. This preliminary work contained the foundations of what would become Principia. Halley was amazed. Convinced that Newton's work should be published, he offered to finance the printing of the book, an extraordinary gesture considering that Halley was not a wealthy man. The arduous writing process. Newton, with his perfectionist character, worked tirelessly on the manuscript. For 2 years he expanded and refined his ideas. What began as a brief treatise on the movement of bodies became a monumental compendium that encompassed 3 books. Each section was more complex than the previous one, but all were connected by a central theme: the mathematical laws that govern the universe. In the first book, Newton established the foundations of classical mechanics, including his famous 3 laws of motion. In the second, he explored the effects of fluids and air resistance, topics that would be relevant to engineering centuries later. But it was the third book, The System of the World, that left the public in awe. Here, Newton applied his theories to explain the movements of planets, tides, and even the trajectories of comets. It was as if he had taken the entire universe and reduced it to a set of elegant equations. When Principia was finally published in 1687, it caused a true revolution. Although its technical language and mathematical complexity made it not accessible to everyone, scientists of the time immediately recognized its importance. Newton had unified terrestrial and celestial physics under a coherent mathematical framework. For the first time, it seemed that the universe functioned like a precise mechanism, governed by universal laws. The law of universal gravitation was, without a doubt, the most striking aspect of the book. The idea that each particle of matter in the universe attracts all others with a force proportional to its mass and inversely proportional to the square of the distance was astonishing. This simple equation explained not only the movement of planets but also phenomena such as tides and the falling of bodies. Despite the success of Principia, the process of creation and publication was not without tensions. Newton was notoriously difficult to deal with and had a history of confrontations with other scientists. During the writing of Principia, he came into conflict with Robert Hooke, who claimed that the idea of universal gravitation belonged to him. Although Hooke did not have solid evidence to support his claim, his insistence deeply irritated Newton. When Newton assumed the presidency of the Royal Society years later, he made sure to erase almost any mention of Hooke from the institution's records. Some historians speculate that he even ordered that a portrait of Hooke be removed from the Society's headquarters. This episode reflects the darker side of Newton's genius, his inability to forgive and forget. Newton at the Royal Mint, hunter of counterfeiters. In 1696, Isaac Newton, the great mathematician and physicist who had redefined the universe with his Principia, found himself in an unexpected place, the Royal Mint of London. For many, the sheet's transition from scientist to government official seemed strange. What was the man who deciphered the mysteries of gravity doing supervising coins? However, for Newton, this change represented a new opportunity, not only to apply his meticulous intellect to a practical problem, but also to face a completely different challenge, the dark and dangerous world of counterfeiting. The call to action. Late 17th century England was immersed in an economic crisis. The kingdom's currency, mostly composed of silver, was being systematically degraded. The edges of coins were scraped to obtain small amounts of metal, and the clipped pieces were then melted down to produce new counterfeit coins. This process, known as clipping, had drastically reduced confidence in English currency, and the financial system was on the verge of collapse. In response to this crisis, Parliament undertook an ambitious national recoinage project. The purpose was to replace all old coins with new pieces that would be more difficult to counterfeit. It was in this context that Newton, then a somewhat isolated academic in Cambridge, was recommended for the position of Warden of the Mint, a position that, although traditionally ceremonial, acquired great importance in these turbulent times. New challenge for a genius. Newton accepted the position in 1696 and moved to London. There, in the bustling heart of the city, he found an environment very different from the quiet university hallways of Cambridge. The Royal Mint, located in the Tower of London, was a place of intense activity. Blacksmiths and craftsmen worked tirelessly to produce new coins, while officials struggled to maintain security and control finances. For Newton, this new environment was a challenge he accepted with enthusiasm. His characteristic approach of precision and dedication soon began to transform the institution. He personally supervised the design and production of the new coins, ensuring that each piece was made with the highest standards of quality. He introduced improvements in the minting processes and adopted measures to make clipping more difficult, such as edges with intricate designs and engravings on the rims. The hunt begins. However, Newton did not limit himself to supervising the minting of coins. His attention turned to an even greater threat: counterfeiters. At that time, counterfeiting currency was a serious offense, punishable by death, but counterfeiters were ingenious and operated in clandestine networks that were difficult to dismantle. To confront them, Newton decided to employ his intellect, with the same rigor with which he had approached the problems of physics. He became more than an administrator. He transformed into an undercover investigator. Newton gathered information, interrogated suspects, and employed informants in the taverns and streets of London to identify the leaders of these criminal networks. He frequently worked until late at night, reviewing legal documents, studying evidence, and developing strategies to prosecute the accused. The case of William Challoner. One of the most notorious counterfeiters of the time was William Challoner, a cunning and ambitious man who had amassed a small fortune manufacturing counterfeit coins. Challoner was a master of deception, known for his ability to evade justice and even for attempting to discredit the Royal Mint through public denunciations. Newton, however, was not intimidated. He carefully studied Challoner's activities, gathering evidence through his informants and witness statements. For months, he built a meticulous case against the counterfeiter, documenting each detail with scientific precision. Finally, in 1699, Challoner was arrested and brought to trial. Newton personally supervised the case, presenting the evidence. with the same relentless logic he had employed in his scientific investigations. The result was conclusive. Challoner was found guilty and sentenced to hang. This case was not only a triumph for Newton, but also a clear message to other counterfeiters that the Royal Mint would not tolerate their activities. Newton's impact on the Royal Mint. During the nearly 30 years that Newton worked at the Royal Mint, first as warden and then as master of the Mint, he transformed the institution into an efficient and modern organization. His meticulous approach and commitment to precision left a lasting mark. Under his leadership, confidence in English currency was restored and the country's financial system stabilized. Additionally, Newton applied his mathematical and scientific knowledge to improve the minting processes, laying the foundations for techniques that are still used today. A different chapter in Newton's life. For many, the years that Newton spent at the Royal Mint are a curiosity in his biography. After all, this was the man who revolutionized physics and mathematics, and his legacy in science easily eclipses his contribution as a government official. However, his time at the Royal Mint reveals a different facet of his personality. A man capable of applying his genius to practical problems and willing to face the challenges of the real world with the same intensity that he dedicated to unraveling the secrets of the universe. In Newton's history, the Royal Mint chapter is proof that even the greatest of intellects can find new horizons, and that genius, when confronted with the most mundane problems, can have a profound and lasting impact. The Knight of Coins and Science. On a cold morning in 1705, Isaac Newton presented himself at Queen Anne's court, dressed in an elegant suit that highlighted his newly acquired position in English society. His days of seclusion in Cambridge and endless calculations by candlelight were behind him. Now, Newton was not only the author of the Principia and the man who had deciphered the mysteries of the cosmos, he was also the master of the Mint, a servant of the kingdom and a knight of the royal order. Newton's transition to the political and administrative world had been unexpected even for him. After decades dedicated to science, he accepted the position of Warden of the Royal Mint in 1696, initially with the intention of retiring from academic tensions and confrontations with rivals like Leibniz. However, what began as a ceremonial position soon transformed into a real responsibility that required his full attention. With a precision and determination that only he could bring, Newton turned the Royal Mint into a bastion of innovation and efficiency. He was not simply a bureaucrat. He was a man of science applying his intellect to the practical world, and the result was an English currency that was more secure, more reliable, and better valued abroad. The honor of knighthood. In 1705, after nearly a decade of service to the Royal Mint, Newton received an honor that would forever change his social status. He was knighted by Queen Anne. This recognition was not common for scientists of the time, and even less so for a man who, although influential, had spent much of his life in intellectual isolation. The ceremony took place in Cambridge, a location that Newton strategically chose to highlight his connection with the university where he had begun his career. In the main hall, surrounded by academics, politicians, and nobles, Newton knelt before the Queen, who touched his shoulder with a ceremonial sword. From that moment on, he was not just Isaac Newton, but Sir Isaac Newton, a title that consolidated him as a key figure in the English nation. The title of knight brought with it an interesting paradox. On one hand, Newton was at the peak of his public career, respected and admired both for his scientific work and for his service to the kingdom. On the other hand, the man who bore the title remained the same introverted, irascible, and meticulous character who had written the laws of motion and obsessively studied alchemy. In the meetings of the Royal Society, where he continued to serve as president, Newton behaved with an authoritarian air that some considered tyrannical. He governed discussions with an iron hand, and few dared to contradict him. However, in his personal life, he remained the same solitary man who preferred to spend his nights reading ancient manuscripts on alchemy or reviewing minute details of the Royal Mint's operations. A legacy divided between science and politics. Newton's position at the Royal Mint not only made him a knight, but also a pillar in England's economic system. Under his leadership, the kingdom rid itself of the threat of counterfeiters and modernized its monetary system. But Newton never ceased to be, in essence, a man of science. While supervising the minting of coins, his mind continued to explore the mysteries of the universe. He still reflected on calculus, optics, and the fundamental forces that maintained the balance of the cosmos. This strange equilibrium between the mundane and the transcendental defined the last years of his life. The eternal night. Although Newton died in 1727, his legacy as the knight of coins and science endures. He was a man who not only transformed physics and mathematics, but also left a profound mark on public administration and the economy of his country. In history books, Sir Isaac Newton appears as a multifaceted genius, a man whose intellect knew no bounds and whose impact extended far beyond the margins of his equations. From the laws of motion to the creation of a modern monetary system, Newton demonstrated that science and administration could coexist, and that even the greatest of geniuses could find new ways to serve his nation. His days as president of the Royal Society. It was 1703, and London breathed a mixture of scientific fervour and political ambition. In this climate of discoveries and disputes, the Royal Society, the most prestigious scientific institution in England, needed a new leader. After years of ups and downs, its reputation was faltering, and members sought someone with the intellect, authority, and prestige necessary to restore its former glory. All eyes turned to Isaac Newton. For Newton, assuming the presidency of the Royal Society represented a unique opportunity. It was not just a position of prestige, it was a stage where he could consolidate his influence, direct the course of English science, and, perhaps most important for his character, settle scores with old rivals. The election of Newton as president was almost unanimous. His fame as the author of the Principia and his achievements in optics had placed him on an untouchable pedestal within the scientific community. Furthermore, his position as master of the Mint made him a figure of political and economic power, someone who could open doors and close debates with a gesture of his hand. From the moment he assumed office, Newton imprinted his seal on the institution. The Royal Society, which had previously been a space for open and sometimes chaotic debates, became under his leadership a well-oiled machine with clear procedures and firm direction. Newton, always meticulous, controlled every detail from figure in the Royal Society for decades. Hooke had died in 1703, the same year Newton assumed the presidency, but his shadow still loomed over the institution. As president, Newton took measures to erase Hooke's legacy. In the archives of the Royal Society, Hooke's portrait mysteriously disappeared, and Hooke's contributions were minimized in official records. Some members of the society whispered about Newton's silent revenge, but no one dared to confront him directly. Despite these personal disputes, Newton's leadership marked a golden era for the Royal Society. Under his direction, the institution sponsored innovative experiments, supported the publication of scientific works, and promoted collaboration among scientists throughout Europe. Newton also used his influence to foster the development of emerging disciplines such as astronomy, chemistry, and biology. He recognized the importance of interdisciplinary science and encouraged society members to explore new areas of knowledge. One of his greatest achievements was the publication of Historia Coelestis, a revolutionary star catalogue that laid the groundwork for the work of astronomers like Edmund Halley. Newton personally supervised this project, ensuring it met the rigorous standards of precision that he himself had established. The tensions with Leibniz. The most dramatic chapter of Newton's presidency was, without doubt, his confrontation with Gottfried Wilhelm Leibniz. The dispute over the invention of calculus had begun years earlier, but reached its peak during Newton's leadership of the Royal Society. In 1712, the Royal Society, under Newton's direction, formed a committee to investigate the accusations of plagiarism that Newton had launched against Leibniz. Although the committee, known as the Committee of Newton's Friends, claimed to be impartial, its final report clearly favored Newton, declaring that he had developed calculus first. Leibniz, outraged, accused Newton of manipulating the process, and using his position as president tipped the scales in his favor. The dispute divided the European scientific community and left scars that endured long after the death of both men. The legacy of a relentless leader. Newton remained president of the Royal Society until his death in 1727, a mandate of almost 25 years that consolidated his place not only as a brilliant scientist, but also as a formidable institutional leader. However, his leadership style was not without criticism. Newton was authoritarian, and his insistence on having absolute control often generated resentment among his colleagues. Some considered him more a politician than a scientist, a man more concerned with protecting his legacy than fostering a true spirit of collaboration. Despite these criticisms, Newton's impact on the Royal Society was undeniable. Under his direction, the institution became the epicenter of English science, a position it would maintain for centuries. In the minutes of the Royal Society, in the projects he supervised, and in the disputes he led, remains the trace of a man who not only unraveled the secrets of the universe, but also fought to shape the scientific community in his image and likeness. Sir Isaac Newton, the relentless scientist and visionary leader, left an indelible mark on the history of science, and on the institution that defined much of his life. Newton and the end of the world, an apocalyptic prophet? Throughout his life, Newton was not only a brilliant mathematician and physicist, but also a devout student of the Bible and an alchemist. In his time, many scientists, like him, sought to interpret the natural world not only as a series of physical laws, but as a manifestation of divine design. Instead of seeing the scriptures as mere religious accounts, Newton treated them as an encrypted text full of cosmic secrets. For him, the scriptures contained codes that, when deciphered correctly, could reveal the mysteries of the universe, and especially the events that would mark the end of times. The obsession with biblical prophecies. Newton was not the only 17th century intellectual who showed interest in the prophecies of the end of the world. During his time, the worldview was strongly influenced by religion, and ideas of an imminent apocalypse were not uncommon. However, Newton took this obsession to a deeper and more mathematical level. Throughout his life, he dedicated more time to the study of the Bible than to physics, despite the fact that his scientific legacy eclipsed his religious work. In particular, Newton focused on the Book of Daniel and the Apocalypse of St. John, two biblical texts that contain numerous apocalyptic visions. Unlike many of his contemporaries who interpreted these passages as mere allegories, Newton was convinced that they contained precise predictions about the future, based on numbers and measurements that could only be deciphered through a logical and mathematical approach. Using the knowledge of science and mathematics that he had developed throughout his career, Newton tried to calculate the exact moment of Christ's return and the end of the world. In his writings, Newton not only focused on historical events, but also made calculations about the duration of the ages of the world according to biblical interpretations. This systematic approach was the same he employed in his scientific research, but applied to the interpretation of sacred scriptures. The calculation of the end of the world. One of the most fascinating areas of Newton's studies on the end of the world was his interpretation of the dates and deadlines established in the Bible. According to Newton, the apocalypse was not just a matter of faith, but could also be understood through mathematical calculations. In his studies, based on the Book of Daniel, he tried to find the exact number of years that would correspond to Daniel's weeks, which represent periods of time in which the kingdom of God would manifest on earth. Newton made assumptions based on the interpretation of the number 1260, which refers to the days of the witnesses in the apocalypse. According to him, these days could be interpreted as years, a common concept among Bible scholars in the Middle Ages. His interpretation of Daniel's weeks led to a fascinating and chilling conclusion. Newton calculated that the end of the world would not occur before the year 2060. This calculation, seemingly logical and mathematical, was not just a hobby for Newton. He was convinced that Christ's return was an inevitable event, and that the scriptures were full of clues for those who could interpret them correctly. However, Newton also made it clear that this event was not something he could predict with absolute certainty, because as in science, there was always uncertainty. In fact, Newton never publicly shared these ideas with the same insistence with which he presented his scientific theories. His studies on apocalyptic prophecies remained largely hidden during his life and were discovered only after his death, which adds an air of mystery to his figure. Alchemy and the end of the world. The study of biblical prophecies was not the only way Newton approached the idea of the end of the world. His passion for alchemy, a marginal science in his time, was also intertwined with his apocalyptic beliefs. Alchemy, which focused on the transmutation of metals and the search for the philosopher's stone, was also imbued with ideas about the transformation of the universe and the final destiny of humanity. For Newton, alchemy was not just a quest for material transmutation, but a way to understand the spiritual and cosmic transmutation that would occur at the end of times. Through his alchemical experiments, Newton tried to find the universal laws that governed the creation of the universe, and he believed that by understanding these laws, he could approach a deeper vision of the end of the world. In his alchemical writings, Newton often referred to the great work that represented the creation and destruction of the universe, a process that would culminate in the final judgment. Through this work, Newton tried to connect science with religion, uniting rational principles with spiritual ones. An apocalyptic prophet or a man of science? When analyzing Newton's life from this perspective, the question arises: was Newton an apocalyptic prophet or a scientist? The answer is, in many respects, both. Although his studies of biblical prophecies and alchemy were marginal compared to his contributions to science, they show a facet of Newton that that was not completely rational or logical, but also deeply religious and obsessed with the mysteries of the universe. Newton saw the universe as a perfectly ordered machine, but also as a divine creation. In this sense, his studies on the end of the world were not a mere curiosity, but an extension of his desire to understand the fundamental nature of the cosmos. He believed that the end of the world was not a random event, but the fulfillment of a divine plan, which he could try to decipher using the tools of science and religion. Although Newton's prophecy about the end of the world has not come true, and probably will not come true in 2060, his efforts to connect science with the divine have left a lasting mark on history. Newton not only redefined our understanding of the physical universe, but also opened a path for science and spirituality to coexist, at least in his mind. A solitary genius, without friends or partner. Isaac Newton, the man who would forever change the course of science, is a fascinating figure for many reasons, but one of the most intriguing is his personal life. While his contributions to physics, mathematics and astronomy have transcended centuries, his emotional and social life remains a mystery. Far from public fame and the hustle and bustle of royal courts or academic circles, Newton lived much of his life in solitude, completely dedicated to his work, and removed from the more human bonds that many of his contemporaries considered essential. Throughout his existence, Newton seemed to be caught in a constant struggle between his genius and his own internal demons. The loneliness of childhood. The story of Newton's life as a solitary genius began long before he made his first scientific discoveries. He was born on December 25, 1642, in a small village called Woolsthorpe in England. From the beginning, his life was marked by the absence of a present maternal figure. His mother, Hannah Ayscough, gave birth to him when she was 19 years old, but his father died 3 months before his birth. After being widowed, his mother remarried another man when Newton was 3 years old. The relationship between mother and son deteriorated considerably as she decided to move in with her new husband and left Newton in the care of his maternal grandparents. This early separation from his mother was just the beginning of a life of emotional isolation. Newton's early years were filled with loneliness and the feeling of being a stranger in his own family. His relationship with his mother was tense, and although it is known that she returned to his life later, they never established a close bond. In his childhood, Newton was considered an introverted and solitary child, more interested in his own thoughts and experiments than in interaction with other children. Accounts of his childhood tell us of a child who preferred to immerse himself in reading and observing nature rather than playing with his peers. University life. An isolated study. When Newton was admitted to Cambridge University in 1661, his social life hardly improved. Despite being in a vibrant academic institution, full of students and professors, Newton preferred the solitude of his room to the camaraderie of others. While many of his peers enjoyed university life, participating in philosophical or social discussions, Newton was busy conducting experiments in his room, devoting himself to studying the works of the greatest thinkers of the time, René Descartes, Galileo Galilei, Johannes Kepler, and others. Although he had access to a rich intellectual life, he did not seem to have an interest in forming deep friendships or joining social conversations. His academic focus was so absorbing that even his professors noticed his inability to connect with others. It is said that Newton was a somewhat bewildering figure to his peers and teachers, who often saw him as a strange young man, engrossed in his thoughts and with a distant attitude. Although his intellect was recognized, his lack of social skills and his solitary focus on his studies gave him the reputation of being eccentric and even somewhat disagreeable. One of the few moments where closer interactions with others are recorded was with the mathematician John Wickens, who was his study companion. However, despite this small bond, Newton continued to work primarily independently. Throughout the years at Cambridge, his solitary character only intensified, which in turn facilitated his immersion in the scientific and philosophical topics that would dominate his life. The absence of friends and romantic relationships. One of the most notable characteristics of Newton's life is that he never married nor had a known romantic partner. Although it is not entirely clear why Newton avoided marriage, some historians suggest that his obsessive focus on his work and his reserved nature led him to have no interest in personal relationships. It is well known that Newton devoted long hours to his research and study, immersed in work to the point of losing track of time and social interactions. It is often said that his experiments and thoughts gave him such satisfaction that any emotional or personal distraction left him indifferent. Throughout his life, Newton maintained very few close friendships. While he corresponded with other scientists such as Robert Hooke, Christopher Wren, and Edmund Halley, his relationships with them were primarily professional and marked by competition. In particular, his relationship with Hooke was tense and conflictive. Newton, known for his strong temperament and stubbornness, had problems sharing the spotlight with others. Despite being aware of his own talent, Newton was not a man who sought social recognition or emotional support from his peers. His behavior often appeared distant and in many cases distrustful of others' intentions. Regarding women, Newton also seems to have been notably indifferent. Although some historians have speculated that he may have had romantic feelings towards certain women, there is no concrete evidence of any romantic relationship. Newton never married, and the lack of records about personal relationships might suggest that, instead of having an active, affective life, scientific work and his religious studies were the only things that truly occupied his mind. The obsession with work and lack of a social life. For Newton, science was a refuge. When immersed in his research, he seemed to forget the outside world. His work notes, written with meticulous precision, reveal that he spent days and nights without rest, making endless calculations and formulating theories that would change history. In fact, some of his deepest investigations, such as his development of the laws of motion and universal gravitation, were carried out in almost total isolation. This extreme dedication to his scientific work is one of the reasons why Newton reached such a high level of brilliance, but it was also the cause of his isolation. His social life was never a priority, and although he achieved great prestige in academic and scientific circles, his achievements were largely the result of his solitary work. It was this obsession with knowledge, this ability to immerse himself in his own intellectual world, that made him a genius, but also emotionally isolated him from others. The figure of Isaac Newton as a solitary genius reminds us that greatness sometimes comes with personal sacrifices. While many of us value company and interpersonal relationships, Newton lived in his own world, one that only he fully understood. In his case, solitude was the price he paid for his incredible discoveries, and for a mind that operated at a level beyond the reach of most of his contemporaries. The last days of a Titan. Newton's ailments. The life of Isaac Newton, one of the greatest geniuses in history, was marked by moments of absolute brilliance, extreme isolation, and, in the end, inevitable physical decline. In his final years, far from the university classrooms and laboratories where he had forged his legacy, Newton spent his days facing the consequences of a life that, although full of monumental discoveries, was also marked by obsession and lack of self-care. As he advanced in age, the man who had unraveled the mysteries of the universe, who had formulated the fundamental laws of physics and mathematics, began to face the physical ailments that reminded him of his human fragility. His obsession with science often led him to forget the basic needs of his body. For years, he suffered from severe stress, depriving himself of sleep and food for the sake of his work. Some historical reports reveal that, on occasions, Newton spent entire days working without rest, something that would eventually take its toll. His lack of rest, combined with the pressure of maintaining his position as president of the Royal Society and his responsibilities as director of the Mint, had a negative impact on his health. The deteriorated physique of a Titan. By the mid-1690s, Newton had already experienced the first considerable physical deterioration. Although his mind remained as sharp as ever, his body was beginning to show the signs of a life marked by lack of self-care and stress. The genius who had once shone with the clarity of a star now faced inevitable aging. His years of obsessive work, his long sleepless nights, and his rare outings in the open air had taken their toll. In particular, Newton suffered from digestive problems. His frequent stomach discomforts were one of the first signs that his health was affected by years of neglect. He suffered from episodes of colic and abdominal pain, which prevented him from living a comfortable life in his old age. It is interesting to note that despite his deep understanding of the physical phenomena that governed the universe, Newton seemed unable to apply that same knowledge to his own physical well-being. Digestive problems were not the only symptoms his body was sending him. He also began to suffer from joint pain and a general loss of energy. But the real blow to his health came in his last years, when Newton's eyesight began to deteriorate. Throughout his life, Newton had dedicated countless hours to detailed observation, whether of the heavens or of everyday objects. His work with telescopes and his research on light and colors required exceptional visual acuity. However, in his old age, that same vision began to fade. Vision problems, which had begun in the 1690s, worsened in his final years, to the point where he was forced to depend on others to read and write. Newton's religious life and his search for answers. As his health deteriorated, Newton began to move increasingly away from science and focused on more spiritual matters. Although he had always had a deep fascination with alchemy and theology, in his later years this spiritual quest intensified. His mind was no longer occupied only by the laws of motion or gravity, but by the idea that his life had a purpose beyond scientific achievements. Newton began to explore biblical texts more deeply, seeking answers to the great questions of existence. For many years, Newton had kept his religious investigations secret, as these were viewed by many of his contemporaries as heretical. His interest in alchemy, in particular, was known in very restricted circles, but as he approached the end of his life, Newton began to speak more openly about his religious beliefs and spiritual doubts. In his later writings, a more introspective Newton is shown less concerned with the laws of nature and more interested in understanding divine mysteries. Some biographers have suggested that this religious quest was not a simple intellectual curiosity, but a way to escape the fear of oblivion or death. Throughout his life, Newton had been so obsessed with the pursuit of knowledge that he had neglected many of the most basic human needs, including emotional ones. Now, in his later years, he seemed to have found comfort in the idea that his work had not only had an impact on science, but also formed part of a larger divine plan. The death of a Titan. Newton's health continued to deteriorate throughout his final years. In 1727, at the age of 84, the great scientist was on his deathbed. Although his mind remained lucid, his body could no longer resist. During the weeks Before his death, Newton was attended by doctors and close friends. In his final moments, he seemed to be at peace, although some sources suggest that he was in a state of semi-unconsciousness due to extreme exhaustion and health complications. On March 20th, 1727, Isaac Newton died at his home in Kensington, London. His death marked the end of an era. The world had lost one of the greatest geniuses in history, but his legacy would continue to live on for centuries. The immortal legacy of a man under a tree. The story of Isaac Newton, the man who changed the course of science and humanity, is tinged with moments of brilliance and mystery. However, one of the most emblematic and often most romantic episodes of his life is the one that takes place under a simple apple tree in the tranquil countryside of his home in Woolsthorpe. This event, seemingly trivial at first glance, has become one of the most celebrated myths in the history of science. Newton, under that tree, not only contemplated a falling apple, but, according to legend, witnessed the flash of understanding that would lead to the formulation of the law of gravity. This chapter in history not only underscores the key moment that allowed Newton to conceptualize one of the most fundamental laws of the universe, but, beyond the anecdote, reveals the profound connection of man with nature, human thought, and the eternal curiosity that pushed him to unravel the mysteries of the cosmos. The legacy of a man under a tree. Newton's legacy, born under the shadow of an apple tree, is immeasurable. The theory of universal gravitation that he developed not only transformed physics but also established the foundations of classical mechanics. This legacy, however, went beyond gravity. Newton laid the groundwork for the laws of motion, which would later inspire scientists like Albert Einstein to expand the understanding of the universe toward the theory of relativity. The legacy of Newton, the man under the tree, lives on today in every advancement of science, in every new question we ask about the universe. His life and discoveries teach us that even in the stillness of a garden, under an apple tree, the most powerful ideas that connect us to the stars can emerge.